Good evening, everyone. Today, we're going to explore a topic that sits at the intersection of physiology, neuroscience, and performance enhancement: how to build muscle size, increase strength, and optimize recovery. We're not just going to talk about sets and reps. We're going to talk about what's happening at the level of your neuromuscular system, your hormonal environment, and the molecular signaling pathways that dictate adaptation. Let's start by laying a framework. There are three distinct yet overlapping physiological goals. 1. Muscle hypertrophy, the increase in size of muscle fibers. 2. Strength development, the nervous system's ability to recruit motor units efficiently. 3. Recovery, the restoration of homeostasis and readiness for subsequent performance. Muscle hypertrophy is a biological process that reflects the body's adaptive response to increased mechanical load. It is not just about lifting heavier weights or spending more time in the gym. At its core, hypertrophy is governed by intracellular signaling cascades, hormonal responses, and gene transcription, all of which respond to the quality and structure of the physical stimulus. When skeletal muscle is subjected to repeated tension, particularly under conditions that challenge homeostasis, specific molecular pathways are activated that initiate protein synthesis and cellular remodeling. The primary mechanisms of hypertrophy include mechanical tension, muscle damage, and metabolic stress. These three stimuli operate synergistically to induce the cascade of molecular events that ultimately lead to the enlargement of muscle fibers. Mechanical tension refers to the force that is generated both actively and passively during muscle contractions, especially during resistance training. When a muscle contracts under load, whether that's through concentric shortening or eccentric lengthening action, it experiences stretch and tension at the sarcomere level. This tension activates mechanosensors located within the cytoskeleton of the muscle fiber. These mechanosensors, particularly focal adhesion kinase, FAK, and integrins, transmit signals that initiate mTOR, mammalian target of rapamycin activation. mTOR is often considered the master regulator of anabolic signaling. It operates as part of a complex that responds to mechanical cues, amino acid availability, especially leucine, and hormonal inputs like insulin and IGF-1. When mTOR is activated, it promotes translation initiation by phosphorylating key proteins involved in protein synthesis, such as P70S6 kinase and 4-EBP1. Over time, this results in an increase in the size of existing muscle fibers, particularly type 2 fast-twitch fibers, which have the greatest potential for growth. Another key factor in hypertrophy is muscle damage, specifically microtrauma to the muscle fibers that occurs during resistance exercise. This damage is not injury in the pathological sense, but rather controlled disruption of the Z-lines within the sarcomeres. When this damage occurs, a local inflammatory response is initiated, bringing immune cells, particularly macrophages and neutrophils, into the muscle tissue. These cells not only clean up cellular debris, but also release growth factors such as IGF-1, FGF, and HGF that stimulate satellite cell activation. Satellite cells are muscle stem cells that reside between the basal lamina and sarcolemma of the muscle fiber. When activated, they proliferate and fuse to existing muscle fibers, donating their nuclei and allowing the muscle to increase its capacity for protein synthesis. This is critical because muscle fibers are multinucleated, and an increase in fiber size requires a proportional increase in the number of nuclei to maintain proper cellular function. The integration of satellite cells into the hypertrophy process highlights the dynamic and regenerative nature of skeletal muscle. Metabolic stress is the third major contributor to hypertrophy. It arises from the accumulation of metabolites such as lactate, hydrogen ions, inorganic phosphate, and reactive oxygen species during anaerobic exercise. This buildup occurs particularly during high-repetition, short-rest training protocols. Metabolic stress enhances the hypertrophic response by promoting increased motor unit recruitment, cellular swelling, and hormonal signaling. The sensation of the pump, often sought after by bodybuilders, is more than anecdotal. It reflects increased intracellular hydration and metabolic byproducts, both of which signal anabolic pathways. Training variables such as volume, intensity, rest periods, and tempo play a significant role in determining the degree of hypertrophy. Studies have shown that training with moderate loads typically in the range of 65% to 85% of 1 rep max, elicits the greatest hypertrophic response. This corresponds to approximately 6 to 12 repetitions per set. It is important that these sets are taken close to muscular failure, as this ensures maximal motor unit recruitment and sufficient mechanical tension. The tempo of each repetition, particularly the eccentric phase, should be controlled. Lengthening contractions under load produce greater muscle damage and are more effective at stimulating growth than concentric-only movements. Training volume, defined as sets x reps x load, is another critical variable. Higher volumes generally lead to greater hypertrophy, up to a point. There is an inverted U relationship, meaning that too little volume won't provide sufficient stimulus, while excessive volume can lead to overtraining and impaired recovery. A good starting point is 10 to 20 total sets per muscle group per week, divided across 2 to 3 sessions. This allows for adequate stimulus while also distributing fatigue and giving sufficient time for recovery and adaptation. Equally important to the training stimulus is the nutritional environment that supports hypertrophy. Protein intake is essential, as amino acids provide the raw materials for muscle repair and growth. Among these, leucine plays a unique role due to its ability to directly stimulate mTOR. Aiming for 1.6 to 2.2 grams of protein per kilogram of body weight per day provides a sufficient range for most individuals engaged in regular resistance training. Spreading protein intake evenly across 3 to 5 meals per day may further enhance muscle protein synthesis by avoiding long periods of low amino acid availability. Carbohydrates, while often debated in fitness circles, play a critical role in hypertrophy as well. They replenish glycogen stores, which fuel high-volume training, and they increase insulin secretion, a hormone that supports nutrient uptake and suppresses muscle protein breakdown. Consuming a mixed meal with protein and carbohydrates post-training enhances the anabolic response by taking advantage of the increased insulin sensitivity that occurs after exercise. Hormonal responses to resistance training also contribute to hypertrophy. Acute spikes in testosterone, growth hormone, and IGF-1 occur following intense exercise, particularly with large compound movements like squats and deadlifts. While the magnitude and duration of these spikes may be transient, they create a hormonal milieu that supports anabolic signaling. Chronic resistance training can also enhance androgen receptor density within muscle tissue, making the muscle more responsive to circulating hormones over time. One often overlooked factor is the nervous system's contribution to hypertrophy. While typically associated with strength, the central nervous system dictates motor unit recruitment. To induce hypertrophy, especially in high-threshold motor units that innervate fast twitch fibers, it is necessary to train with sufficient intensity and intent. Performing each repetition with focus and maximal voluntary effort enhances cortical engagement and neuromuscular efficiency. In other words, lifting with deliberate intention, rather than going through the motions, makes a measurable difference in the quality of the adaptation. Finally, hypertrophy is a process that accumulates over time. It requires consistency, progression, and adequate recovery. The cellular machinery responsible for building muscle does not operate in isolation. It is influenced by sleep, stress, hydration, and even psychological mindset. Chronic stress and sleep deprivation elevate cortisol and impair anabolic signaling, while quality sleep, especially deep non-REM sleep, enhances growth hormone secretion and protein synthesis. Strength is fundamentally a neural phenomenon before it becomes a muscular one. While muscle size and cross-sectional area certainly contribute to force production, the primary adaptations that lead to increased strength occur within the nervous system. To understand how to build strength effectively, it's important to examine the neurophysiological mechanisms that control voluntary movement and force output. The central nervous system, consisting of the brain and spinal cord, orchestrates the recruitment of motor units, individual motor neurons, and the muscle fibers they innervate. When you exert force, whether it's lifting a barbell or bracing your body, your brain is sending rapid patterned electrical signals to specific muscles. These signals travel down the corticospinal tract, synapse onto alpha motor neurons in the spinal cord, and activate muscle fibers through neuromuscular junctions. One of the core principles in strength development is motor unit recruitment. Motor units follow the size principle, meaning that smaller low-threshold units are recruited first. These typically activate slow-twitch, fatigue-resistant fibers. As force demands increase, larger high-threshold motor units are recruited, which control fast-twitch muscle fibers capable of producing greater force. Strength training, especially at high intensities, trains the nervous system to bypass or rapidly progress through the lower threshold units to recruit high-threshold motor units more efficiently. This ability to tap into maximal motor unit potential is one of the hallmarks of advanced strength adaptation. Rate coding, or the frequency at which a motor neuron fires action potentials, also plays a critical role. Increased rate coding means that the neuron is firing at a higher frequency, resulting in greater force production from the associated muscle fibers. Strength training enhances rate coding by conditioning the nervous system to sustain high-firing frequencies under load. Another neural adaptation that contributes to strength is synchronization. While motor units typically fire asynchronously to produce smooth movements, strength training can enhance the synchronized firing of multiple motor units during maximal efforts, leading to more forceful contractions. Intermuscular coordination is another often overlooked, yet vital component of strength development. This refers to the ability of multiple muscles and muscle groups to work together in a coordinated fashion to stabilize joints and generate movement efficiently. For instance, in a compound movement like a squat, the coordination between the quadriceps, hamstrings, glutes, lower back, and core muscles is essential for both safety and performance. Strength training refines these neural patterns, reducing co-contraction of antagonist muscles and improving the timing and sequencing of muscle activation. To effectively target these neural adaptations, the structure of training must differ significantly from protocols focused on hypertrophy or endurance. The most effective strength training programs use low repetition ranges, typically 1 to 5 reps per set, with high loads ranging from 80% to 95% of 1 rep max. These heavy loads provide the stimulus necessary to engage the central nerve at a high level. The key here is not just the absolute weight, but the intensity of effort and the intent to move explosively, even if the bar speed is slow due to the heavy load. This intent primes the nervous system to recruit high-threshold motor units more effectively. Rest intervals in strength training must also reflect the goal of neural adaptation. Short rest periods do not allow for sufficient recovery of the nervous system, particularly the resynthesis of neurotransmitters, like acetylcholine, and the rebalancing of central fatigue factors. Longer rest intervals, generally between 2 to 5 minutes, allow for more complete recovery between sets, enabling each effort to be executed with maximal focus and force production. This is essential because quality of output is more important than quantity when training for strength. The choice of exercises is also critical. Multi-joint, compound lifts such as the squat, deadlift, bench press, overhead press, and barbell row are foundational because they engage large muscle groups and require substantial coordination and stability. These movements place high demands on the nervous system and allow for progressive overload across a wide range of intensities. They also allow for the development of movement patterns that carry over into sport, occupational tasks, and daily life. Barbell training provides a unique stimulus due to its loadability and stability requirements. The barbell acts as a tool that amplifies feedback to the nervous system, teaching precise control and positioning. Over time, small adjustments in bar path, joint angle, and muscle activation can lead to measurable improvements in efficiency and strength output. Variations of these compound lifts, such as tempo squats, pause deadlifts, and close grip bench presses, can be used to target weak points in the range of motion and further refine neuromuscular control. A key component of strength development is autoregulation, adjusting training based on readiness and fatigue. The nervous system does not respond well to excessive volume or accumulated fatigue when the goal is maximal strength. Using techniques like rate of perceived exertion, RPE, or velocity-based training can help ensure that intensity remains high without exceeding recovery capacity. Fatigue management becomes critical, as central nervous system fatigue can impair coordination, reduce rate of force development, and increase injury risk. Another neural adaptation associated with strength is improved inhibitory control. The human body is equipped with protective mechanisms, like the Golgi tendon organ reflex, that limit excessive force output to protect joints and tendons. With repeated exposure to high loads, the sensitivity of these inhibitory reflexes can decrease, allowing the nervous system to tolerate and produce greater force outputs without prematurely shutting down muscular effort. This desensitization contributes to the progressive increases in maximal strength seen with consistent high-intensity training. In terms of hormonal and neurotransmitter activity, heavy resistance training promotes transient elevations in testosterone, epinephrine, and dopamine. These chemicals enhance focus, energy mobilization, and mood. The dopaminergic system, in particular, is highly involved in goal-directed behavior and motor learning. Elevated dopamine levels increase motivation and reinforce neural patterns related to strength tasks. The prefrontal cortex and basal ganglia interact to fine-tune motor output and motor learning, which are key in developing strength through repeated exposure to skilled movement under load. Motor learning is often underestimated in the context of strength training. Each repetition performed is a rep of skill acquisition. Especially in novice and intermediate lifters, a substantial portion of early strength gains comes not from muscle growth, but from improved efficiency movement. As the brain becomes more adept at predicting and controlling the outcomes of movement, performance improves. This is why practicing with submaximal loads at high velocity, sometimes referred to as dynamic effort work, can improve the rate of force development and movement efficiency without incurring the same fatigue as maximal loading. Breathing, bracing, and spinal stability are integral to strength development, particularly in axial loaded movements. Proper diaphragmatic breathing increases intra-abdominal pressure, stabilizes the spine, and allows for more efficient force transfer through the kinetic chain. This is coordinated by both autonomic and voluntary nervous system activity. Learning to coordinate breath and bracing in conjunction with movement is a skill that becomes increasingly important as load intensifies. Recovery and strength-focused training requires special attention to neural restoration. While muscular recovery might occur within 24 to 48 hours, the nervous system, particularly at higher intensities, may require longer. Strategies such as sleep optimization, strategic deloads, and the use of contrast therapies can support neural recovery. Adequate micronutrient intake, especially of B vitamins, magnesium, and omega-3 fatty acids, supports neurotransmitter synthesis and myelin sheath integrity, both of which are relevant for optimal nervous system function. Neuroplasticity, the brain's ability to change in response to repeated stimulation, is foundational to all of these processes. Strength training, when performed with intention and precision, leverages neuroplasticity to improve communication between the brain and muscles. Each exposure to high-resistance training reinforces the circuits involved in motor control, balance, stability, and force production. Over time, this produces a more robust, responsive, and powerful neuromuscular system. Recovery is a physiological process that restores balance and readiness following training-induced stress. While training is the stimulus that drives adaptation, recovery is the phase where those adaptations are solidified. Without adequate recovery, even the most well-structured training protocol will eventually result in diminishing returns, stagnation, or injury. Recovery is not passive, it is an active biological recalibration involving the nervous system, endocrine system, immune response, and cellular regeneration. A critical first step in understanding recovery is recognizing the role of the autonomic nervous system, which has two primary branches, the sympathetic and the parasympathetic. The sympathetic system is often referred to as the fight or flight mode. It dominates during training and acute stress, increasing heart rate, blood pressure, and glucose availability. The parasympathetic system, on the other hand, governs the rest and digest state. Recovery depends heavily on the transition from sympathetic dominance to parasympathetic activation. The faster and more effectively this shift occurs post-training, the quicker the body can begin repair processes. One of the most effective ways to facilitate this shift is through deliberate control of the breath. Slow nasal, diaphragmatic breathing, especially exhalation-focused patterns, stimulates the vagus nerve, which enhances parasympathetic tone. Practicing 1 to 3 minutes of slow breathing immediately post-training or before sleep can accelerate autonomic recovery. The vagus nerve serves as a communication highway between the brain and internal organs, and its activation supports heart rate variability, digestion, immune response, and inflammation regulation, all of which are essential during recovery periods. Sleep is the most powerful and underutilized tool for recovery. During sleep, especially during slow-wave non-REM sleep, the body undergoes profound anabolic and regenerative processes. Growth hormone is secreted in pulsatile bursts during the early parts of the night, driving protein synthesis, muscle repair, and connective tissue regeneration. Additionally, sleep supports memory consolidation, motor learning, and emotional regulation, factors that influence training performance both directly and indirectly. The architecture of sleep matters. Cycles of deep sleep, followed by REM, provide complementary benefits. Deep sleep restores the body. REM enhances neural recalibration and cognitive processing. Circadian alignment plays a crucial role in optimizing sleep quality and, by extension, recovery. The body operates on a roughly 24-hour cycle, regulated by the suprachiasmatic nucleus of the hypothalamus. This internal clock is entrained by external cues, the most potent of which is light. Exposure to natural sunlight, especially within the first hour of waking, anchors circadian rhythms, increases morning cortisol, which is healthy when elevated early in the day, and promotes melatonin production later in the evening. Avoiding artificial light, particularly blue light, from screens in the hours before sleep prevents disruption of melatonin release and helps maintain deep, continuous sleep. Beyond sleep, nutritional inputs are fundamental for recovery. The period following training is marked by increased insulin sensitivity and greater nutrient uptake into muscle tissue. Consuming a meal containing both protein and carbohydrates after training can support glycogen resynthesis and muscle protein synthesis. Protein intake during recovery should meet the threshold necessary to stimulate the mTOR pathway and maintain a positive nitrogen balance. Ingesting 20 to 40 grams of high-quality protein, especially those rich in leucine, such as whey, eggs, or lean, promotes muscle repair. Including slow-digesting carbohydrates aids in restoring glycogen and lowering cortisol. Micronutrients also influence recovery through their effects on inflammation, mitochondrial function, and neurotransmitter synthesis. Magnesium, for example, supports over 300 enzymatic processes and plays a role in neuromuscular function and parasympathetic regulation. Omega-3 fatty acids, particularly EPA and DHA, reduce systemic inflammation and have been shown to decrease muscle soreness and improve range of motion after eccentric training. Adequate intake of B vitamins supports energy production and tissue repair, while antioxidants such as vitamin C and E help modulate oxidative stress, though their use should be timed carefully, as excessive antioxidant supplementation immediately after training may blunt adaptive signaling. Hydration is another essential component of recovery. Water supports cellular function, thermoregulation, nutrient transport, and joint lubrication. Even mild dehydration can impair performance and delay recovery. Electrolytes, particularly sodium, potassium, calcium, and magnesium, must be maintained within optimal ranges to preserve nerve conduction and muscle function. Sweat losses during training sessions can vary based on intensity, climate, and individual sweat rates. Post-exercise hydration should aim to restore fluid balance with a combination of water and electrolytes, not just plain water. To avoid dilutional imbalance, the immune system is actively involved in the recovery process. Exercise creates localized inflammation in muscle and connective tissue, which is a necessary. Immune cells migrate to these areas, clear debris, and release cytokines and growth factors that support regeneration. However, if systemic inflammation remains elevated chronically due to poor diet, inadequate sleep, or overtraining, it can impair muscle recovery and increase susceptibility to illness. Managing stress through both physiological and psychological interventions is key to balancing inflammation. Practices like meditation, journaling, or spending time in nature can reduce cortisol levels and enhance overall recovery. Cold exposure has been widely discussed as a recovery tool. Cold water immersion can reduce perceived muscle soreness and decrease inflammation in the short term. However, it is important to consider timing. If the goal is hypertrophy or strength adaptation, applying cold therapy immediately after training may blunt anabolic signaling by suppressing mTOR activity and local inflammation, both of which are necessary for muscle growth. Cold exposure may be more beneficial when used hours after training or on rest days, rather than immediately post-exercise. Heat exposure, on the other hand, can complement recovery by increasing circulation, promoting heat shock protein expression, and supporting tissue pliability. Regular sauna use has been associated with increased endurance, reduced delayed onset muscle soreness, DOMS, and improved cardiovascular health. Heat stress also stimulates the release of growth hormone and supports parasympathetic activation, which together enhance overall recovery. Alternating heat and cold exposure, often referred to as contrast therapy, may provide synergistic effects for circulation and autonomic balance. Movement itself can be a powerful recovery tool. Low-intensity cardiovascular activity, often termed active recovery, increases blood flow to muscle, helps remove metabolic byproducts, and enhances lymphatic drainage. Activities like walking, swimming, cycling, or yoga, performed at conversational pace, stimulate recovery without adding systemic stress. Movement also contributes to synovial fluid circulation in joints, maintaining mobility and reducing stiffness post-training. Incorporating active recovery days into a weekly schedule allows continued progress without accumulating excess fatigue. Sleep, nutrition, hydration, and movement form the biological foundation of recovery, but psychological recovery is equally important. Mental fatigue and emotional stress activate the same sympathetic pathways as physical stress. High levels of psychological stress increase cortisol, impair sleep, and reduce motivation and adherence to training programs. Addressing mental recovery through stress management practices, digital detox, creative engagement, or social connection supports the physiological aspects of recovery. The prefrontal cortex, responsible for decision-making and focus, becomes less efficient under chronic stress, affecting everything from reaction time to training quality. Recovery is also modulated by individual variability. Genetic differences in collagen synthesis, immune response, hormonal regulation, and circadian rhythms can all influence recovery speed and capacity. Some individuals may require more sleep or longer periods between high-intensity training sessions. Tracking key indicators, such as resting heart rate variability, sleep quality, and subjective readiness, can help tailor recovery protocols to the individual. Tools like wearable devices, recovery logs, or simple morning check-ins can provide useful feedback on when to push and when to scale back. Recovery is not merely about doing less. It is about creating the optimal environment for adaptation. The tissues that are broken down during training must be rebuilt stronger, and that requires not only time, but resources. Energy, nutrients, hormones, and neural input all play roles in orchestrating this complex biological process. Respecting the role of recovery in the training cycle is not a sign of weakness, but a strategy for sustainability and long-term progression. A system that is constantly stressed without recovery will eventually resist growth and become vulnerable to breakdown. The human body, when given the right conditions, is remarkably efficient at repairing, adapting, and coming back stronger.